Hello, my name's Sam Ammons. I've got some Enigma Cipher computers here that I built, and I'd like to show you briefly how the Enigma process works, since I have two of them. And it's very rare to have two on the same table, so I figure I may as well take advantage of this. Make a quick video on how the Enigma works, specifically how the ones that I created works. Here, as we see, are two Enigma Cipher machines. These are 3D printed Cipher machines that I printed up on my Stratasys 3D printers, and made myself some electronics, the circuit boards, and wrote all the softwares to decode German messages from World War II or to encrypt your own new messages. Your basic Enigma, this is a full-sized Enigma, and it did not have this computer display on the front, but it has 26 keys, a strange layout because it was one of the first computers, or rather one of the first cipher machines ever made. Its origins were the banking industry. They didn't really know how to do a keyboard, so they put the letters in what they thought would be the most useful way. So you'll notice it says it's spelled differently than the computers we use nowadays. There's only 26 letters. There are no periods. There's no commas. There's no punctuation. On the front of the Enigma is a patch panel, and the patch panel remaps the front keys so that if you were to type a Q, if you had a patch cable plugged in from Q to W, every time you pressed a Q, it would go into the machine as a W, and every time a W came out of the machine, it would go back in and light up the Q light. So that's what the patch panel does. We have this is a key lock, which I am using as a mode switch, as well as just to keep from putting strange computer switches on top of an older recreation. In here we have the power jack. The power jack is used to supply battery power from a submarine to the unit, so that when you run off of a battery, they run off the batteries, or they run off of the main voltage in a submarine using a cable like this. They would plug that into that, and that would be plugged into 4 volts for the battery power. So here we have two machines. To turn them on, there's a power switch on the battery right here. So you turn the battery on, and the computer says Enigma, and then it says what the ROM checksum is. That way you know if your ROM is damaged and you have any sort of problems with the software. On the second Enigma, we'll go ahead and turn that on. It comes up, and this version of the ROM has that checksum. So I'll put the cover back on. So usually during the start of the day, the German communications officer would choose which of 8 rotors were going to go in the machine. He had a selection of 8 rotors, and they went into positions 1, 2, and 3. So you could have rotor type number 1, rotor type number 7, rotor type number 4. You never really had 4 of rotor types 1, because each submarine only had 1 of each type of rotor. The last rotor, which is called the thin wheel, is one of 2 types. It's either a beta or a gamma rotor. This machine and this recreation will do all of the machines from World War II. It will do the German subs or the Army and Air Force machines, which were generally 3 rotor machines. To select the machine type, you would take this is usually a key lock, but if you've collect it or switch it over to the left, it asks you which machine type you want. This is a 4-rotor machine with a B-type reflector. You could choose a 4-rotor machine with a C-type reflector, 4-rotor machine, 3-rotor machine, another 3-motor machine with a B reflector, or 4. So we're going to go ahead and choose M4 with a UKW of B. That's a reflector type of B. And then you choose your wheel order. Wheel order, if we want rotor number 1, rotor number 2, rotor number 3, and the beta wheel, we would leave it that way. Or if we want to, say, put rotor number 3 over here, rotor number 4 there, and rotor number 5 here, and change the beta to a gamma rotor, that's what we would do. Then we set our ring settings. The ring settings were used to set where A was A on the rotor. If you have a setting of 1, A equals A. If you set it to 3, then C actually equals A. This is the equivalent of rotating the alphabet wheel on the rotor, and it's just changing the label. It's not super sophisticated, but it was something that the Germans could do to obfuscate the message. So you set your rotors with your ring settings, and all these settings were in a code book, which they referred to each day. And they would break out the code book, and they would set their settings, and then they'd encrypt their messages. The next one is the patch panel. This has a software patch panel on it, and for example, if we wanted all of Q's to be remapped to W's, we put QW in. So now if we review that again, by rotating our knob, QW will say E equals R. We can go back again and go QR, EW, let's try that again, ER, QW, we'll try UI, and then we review it, ER, IU, QW. If we wanted to remove something, we would map Q to Q, and what it would do is it would remove that patch. Notice QW was removed. So after you set up all your machines, you can verify your settings, and then you start off with your ground settings. These are the settings that you start for that message. A lot of times in the code manuals, they may specify you come up with the start settings yourself. Usually the operators would come up with something, and they would say, okay, we're going to use this combination here, which could be, okay, we're going to start our messages with JDFG. The other person on the other end would set their machine up with the same ground settings, the same ring settings, all of the same settings, and then they would be able to decrypt the message. If you don't have all of the settings exactly right, all of the rings, all of the rotors, everything exactly as it is on the other side, it's unlikely or very difficult that you would be able to decipher it if you use proper communications techniques. So to reset the machine back to its original settings, I'm going to turn this machine off. This one is not built into that power switch, so we're going to turn it off here. Turn it back on. Okay, so now this machine is set up with rotors 1, 2, 3 and a 4-rotor machine. We'll go over to the other machine, which is already turned on. So if we want to encrypt a message such as dog, we would press the D key, and the D is routed through the patch panel, which in this case does not have any wires on it, goes into the first rotor, goes out through the D terminal, comes out through another terminal, goes into the second rotor on that terminal, comes out of that rotor on a different one, and makes its way through the last rotor where it gets turned around and goes back through another path to go back through the rotor, which comes back around through the patch panel and then goes to the light and lights the O. So in this case, a D encrypted equals an O. So we'll write down an O, and that's what would be transmitted. So D, now we'll try O for the O in dog, and we get an L. And then we'll get a G, it comes out as an M. So you can see our DOG ended up coming out as OLM. The message would be given to the operator, where they would transmit it using Morse code to the receiving station. The receiving station would set up their machine in the exact same way as the code book, and they would enter O. You'll see the D lights up, so you get a D. Then you write an L, and you'll notice you get an O. And then they'll do a G. Oops, in this case I should have entered M. So what I do is I'll rotate this back. Okay, A worked, B worked, and then I think the starting position would be C, in which case when I put the M in, I get the G. So we can see where OLM has now turned into DOG. The period on the machine is 65,000, roughly 65,000 characters. So if you were to just type A 65,000 times, eventually the cipher sequence would repeat because the rotors would step and they would start repeating. You'll also notice that when you look at the letter settings, every time you type a letter, it advances the first rotor. The first rotor will rotate the second rotor at a fixed position, which differs based upon the rotor type. You'd think it would do it at Z, but it doesn't. Some rotors did it at R, some at M. If we keep watching, you'll see the second rotor turned over to B. The second rotor rotates the third rotor at a different time also. The fourth rotor did not get ever rotated. Sometimes the people in Finland, the Finns, they would actually change the slow rotor, which is on the left. They would change it after every 5 characters. They just bump it up 1. That was called finning, and you think it would make the message even harder to confuse, but cryptology is kind of strange in that it actually made it easier to derive the code sequence. So that's a brief tour of how the Enigma was operated. Now I'm going to show you the insides of the Enigma kit. We're going to go ahead and turn this off. Okay, this is the, I guess, the second Enigma that I've ever built. And inside we'll see the rotor assemblies. There's rotor number 1, rotor number 2, rotor number 3, rotor number 4. We have the switch assemblies. As you can see, when you turn the switch, it's actuated by the movement of the thumb wheel. This tells the microprocessor that the switch was rotated. The actual thumb wheels and rotors in the genuine Enigma, they only turned one way. This one turns both ways, but the switch only increments because I only have the increment switches installed. If I had decrement switches installed, then it would decrement also. Here's the fourth rotor. These rotors are not removable. Well, they're not supposed to be removable, but if you pop this axle out, then you could. Nothing real redeeming about it other than they're pretty much the shape that the original rotors were in the dimensions, and they're just there to make it realistically operated. There are no electrical contacts in this particular set of rotors. Over here we have the microprocessor. This is a Motorola 6811. I wrote the software, patched the operating system so that the Enigma program would automatically start on power up. We have a serial interface which goes to your host computer so that if you want to enter messages offline or online, you can dump the messages into the Enigma and they'll print them out on your notepad. We have the keyboard. The keyboard is here, where we have all the keyboard row and column selects. This is all done with hardware. The micro pretty much reads the keys and the rows, determines which key is pressed. Here's the lamp board. The lamp board is designed so that I write a row and a column and which lights are supposed to be on. Over here we have the back of the display board. We have a lithium ion rechargeable battery, which is typically used for cell phones. They run at 5 volts, which is what the micro runs at, so it's a perfect marriage of current technology and a very lightweight battery. This battery will run this computer probably for about 24 hours continuous. A lot longer if you turn it off when you're not using it. And here we have the wires where I've hidden the power jack and the computer interface cable inside of the power jack. The power jack is usually just a positive and negative terminal, but in this case we use the stereo headphone jack that has a tip, a ring, and a shell. When we use a cable, we use a standard cable like this. This plugs into the Enigma, which then plugs into USB, which is basically, it's just USB power. There's no USB data that comes over that. So that is how you charge it. You just plug that into the wall. You can plug your second Enigma into here if you happen to have two of these. This plugs into your COM port or your serial port adapter or console interface. You get data and data in and out on pins 2 and 3. Wire number 5 is ground, and we also have on pin 8 a Morse code interface so that the machine will transmit the Morse code, the actual Morse code letters, through a keyer program, which you can get off of the internet or write yourself or make your own interface. So you could actually send Morse code and keyboard Morse code from the local keyboard. Looking at the second Enigma, we'll go ahead and turn that off. The second Enigma is serial number 3. And serial number 3 is a little bit different, and it has more extensive use of 3D printed rotors. Here you'll notice that the support is made out of 3D printed plastic. Same with brackets, the switch enclosures. Polish those up a little bit. The goal is to make a template that bolts onto the base plate of this. The rest of the electronics are the same, but I believe I've hit it right on making any changes incrementally to these parts and then implementing them into the next serial number. So you can't really go back and redo the other Enigmas that you did, so you have to pick a point and move forward from there. The battery's held in place by Velcro. It's very lightweight. I'll just leave that stuck on there, but it's very lightweight. And once again, it lasts for 24 hours. This particular battery can power your cell phone as well as your computer. So what else can I say? Here's the back of the patch panel. As you can see, there are no wires on the patch panel because it's a computer. It has a software patch panel, so you don't really need the wires unless you just want the decorative purposes. The cases are made out of 3D plastic, or 3D printed, or this lid is 3D printed plastic. The sides are sheet styrene, which you can get at a hobby store because it's cheaper and easier to print large pieces of a model in styrene and the specialized pieces in the ABS plastic. This is ABS plastic. It's covered with let's see if this is, no, this one here is just plastic, but I have covered them with copper tape to give them a metal look, and it looks really good when you cover it with a metal tape and then paint the metal tape, because it looks like metal. The lamp frames in this case are done with metal tape, which is overlaid on top of the plastic part. You sand the plastic part, you lay the silver tape over it, and then you press it in with your fingers. Mount your screws. Screws go very well into the ABS, and these illuminated from behind. This works very well with those LED lights that you get out of rope lights. That's what I used. Crinkle paint. You can see the crinkle paint on these keys. That was done by using crinkle paint. You can buy it in AutoZone or your local hobby shop. These are RCA jacks, which you can buy off of eBay. They're included with the kit, but when you buy them in bags of a couple hundred, you can end up getting the cost of these down low enough that you can actually put them on there. They're chrome. They're pretty much the same dimension as the genuine Enigma, and you'll notice I don't have the screws installed. I had to take them out to do the demo, and I got a little bit of touch-up paint to do before sending this off. But that completes the demonstration of the Enigma. It's being sold on eBay. All you have to do is Google Enigma Cipher machine, and you'll be able to see the kit. And I'm hoping to offer 3D printed models, fully assembled, as well as the kit if you want to tackle building the kit yourself, which is a major learning experience. you're welcome to it. Or you can have me build it. I've built a couple of them, and I know all the tricks that you are going to need. So thank you very much, and you can send your comments to sam@3dbwireless.com or ihatespam@mcsinternet.net. Thank you very much for watching my video.